This is video 26 in the series on reinforced concrete slabs. We will talk about corbels and the method of strut and tie models. A typical corbel for a beam can have this type of strut and tie model. This is the support, and you will see that the compression strut is doing this, and the tension strut or the tension tie is this. But this is not sufficient. You have compression and you have tension, but then you should use the whole beam. So you have a tension tie here and a tension tie there, and an additional compression strut combining those two together, tying it in fact in. Because of this strut, compression strut, you will have tension perpendicular to that. This is a typical reinforcement of a corbel like we have seen just now. You see it's really getting crowded, and it should be designed with a lot of care. You see here the tie in with stirrups. You see here again the reinforcement needed for the splitting forces in the strut. You can also have two corbels joined together. Then you have the same reinforcement of same type of reinforcement. A column corbel can have different shapes. This is the most used shape in a column corbel, or you can also have this chamfer, because the concrete underneath here is not used. Or you can have types like this, but all three of them are column corbels. You can also have a beam corbel where two beams are joined together, or of course a wall corbel where, for instance, a slab of a precast hollow core slab is put against a wall, a supporting wall. This is a typical configuration of the reinforcement of a column corbel. The main reinforcement is this tension reinforcement, this one. That's the main, most important reinforcement. Depending on the dimensions of the corbel, you need horizontal stirrups or vertical stirrups. Now let's consider a corbel. When you load it, then with every vertical load, there is always a horizontal load that you have to take into account. So a corbel with only a vertical load does not exist. There is always a horizontal load, and even if it is an accidental horizontal load. When you got a system like that and the loads are increasing, then you will see that there are cracks developing like here, like this, but there are also cracks developing within the corbel like that. But this corner here is unaffected, even if those values are very high. So this column is not affected, so why should we put concrete there? Because it's not used. So that's why there's a chamfer on a corbel. It's also for the shuttering to remove it much easier, but you don't need it structurally. You can have now a corbel in a B zone or a corbel in a D zone. When it's in a B zone, then we do not talk about a corbel, but we talk about a cantilever load transfer system. So this is just the load creates a bending moment, and you are just going to put the reinforcement to take up that bending moment. That's just like for beams, no problem at all. On the other hand, you can have a corbel load transfer, and you cannot apply your formulas for beams. You need a strut and tie model. The difference between those two models is that the cantilever load transfer is there when AC, which is the distance of the load to the face of the column when AC is bigger than a value Z0, and Z0 is the distance between the cross section of between the intersection of the compression strut with the face of the column and the tension tie with the face of the column. So this distance is Z0. When AC is bigger than Z0, it's a cantilever load transfer. When AC is smaller than Z0, then you have a Corbel load transfer. Now let's look at the Corbel load transfer. Eurocode 2 proposes this strut and tie model, and we will work this model. We will work with this model. Notice that you have a node here and that you have an eccentricity because of the age, that you have an eccentricity here for the starting point of the strut, the main strut. There are some conditions. The tangent theta must always between 1 and 2.5. The horizontal force must be larger than 1/5 of the vertical force. Z0 is calculated by iteration because you don't know just from the start where Z0 is, because Z0 is the distance between 2 points. The first point is the intersection of the tension tie with the column, in the face of the column, and the compression strut with the face of the column. So this distance, you have to start with a value, and we recommend that you start with a value of 0.85 times the total height of the corbel. The designing a corbel is difficult in the sense that there are a lot of variables that you have to choose. So only with a lot of experience you can design a nice corbel. But to help you in that, we can give you some recommendations. And we say that the total height of the corbel, a suitable total height, is the distance of the load to the face of the column divided by 0.85. That's a suitable distance of a suitable height of the corbel. Then the distance of the load to the face of the column should be smaller than D. We recommend to take 0.4 to 0.6 times D, and D is this distance. L should be smaller than 0.7 H. LC, it should be noted LC is smaller than 0.7 H. And then H0, this value should be bigger than AC and bigger than HC over 2. And Y0, which is the center width of the tension tie, is equal to AC minus D. Z should be taken as 0.9 D, and C is 0.1 or 1/10 of the value D. So it gives you some idea of how to put some dimensions to a corbel to start with. Now, let's put some formulas against it. You have a corbel and there is a load like that, FED and HED. And where this load, the line through this load is has a intersection with the axis of the tension tie, then this distance is called E, which is the eccentricity, in fact, this distance. We already explained what Z0 was. Then at the bottom you have a node. This node has a dimension x1 and y1. We don't know it yet. But what we can do is we can work the other way around, and we can say, okay, we will take x1 and y1 in such a way that the stresses in the concrete are maximized, so that the stresses are allowed in those two elements. If you do not so, you have to guess the dimensions of the node, then do the calculations and check if the stresses are okay. So D1 is then, of course, the concrete cover. Add up the point of gravity of the tension tie, plus when there are vertical stirrups, the diameter of the vertical stirrup. D is then the total height of the corbel minus D1, and Z, this Z is then D minus Y1 divided by 2, and the eccentricity is then of course equal to this formula. HB is the height of the support. The distance A is then equal to the distance AC plus x1 divided by 2. Consider now the two triangles marked here in red. And we see that the angle alpha is that those two angles are equal to alpha. The distance here of the smallest triangle, or the length of the smallest triangle, is Z0. The other side of this triangle is AC, which is this distance, plus the eccentricity E. The total height of this triangle is of course equal to Z, and the total length in the other direction is the A plus the eccentricity E. Now the tangents of this of alpha is then equal to AC plus E divided by Z0, and also is equal to this tangents alpha, A plus E divided by Z. Now we have the relationship that gives us Z0 in function of Z and the geometric parameters. AC is known from the beginning, E also, because this is coming from the value of F of the vertical load and the horizontal load, and A is not known yet because in the definition of A there is half of the width of the knot included. So we'll see how we cope with that. We do that by taking the allowable stress in the nodes with compression and tension. Then the maximum allowable stress is K2 times nu FCD. With nu, we know that this is the expression for nu, and K2 is 0.85 because of its compression and tension combined. And FCD is alpha CC, FCK divided by gamma C, and alpha CC is 1 for struts and ties. In the node number 2, then we have, that's on the top, it's the vertical load. It's divided, of course, by the support dimensions of the support block dimensions AB times BB, and this must be smaller than sigma 2 R max, which is 0.85 times nu FCD. The allowable stress in compression nodes is equals to nu FCD because K1 is 1. The compression nodes is at the bottom of the corbel. This is a node at the bottom of the corbel. This node has a force Fk horizontal and a vertical force Fed, because Fed is equal to this acting force because of the vertical equilibrium. So Fed, that's known, and Fk, this is equal, Fk is equal to the difference between FTD, the tension force in the tie, minus the load HED. So the size of X1 times the width of the effective width of the corbel times the maximum allowable compression stress is equal to FED. So what we do is we are calculating a dimension x1 in such a way that the node is fulfilling the requirements regarding compression stress. We do not use the real width of the corbel, because when the width of the corbel is, for instance, 4 meters, it's not the whole 4 meters that will participate to the resistance. So that's why we use an effective width, and the effective width is of course the minimum of the actual width, or it will be the width of the support plus 2 times the concrete cover plus 2 times a diameter size that we use. So this is a minimum width, or a width that we say that this width takes part in the resistance of the loads. Y1 is then Fk, the horizontal force, divided by the BC effective times the allowable stress. And like we said, Fk is FTD minus HED. Then we take a rotational equilibrium around the point where the strut is hitting the node on the bottom. And around that point, we take the rotational equilibrium, which is, of course, FED, the vertical load FED, times the distance to this blue line, which is A. So it's FTD plus times FTD multiplied by A, plus the horizontal force with this distance, and this distance equals Z plus D1 and plus, of course, the height of the support. Most of the time this can be neglected, HB. And Z is the effective depth D minus A1 over 2. Now we have two equations, and in those two equations we are looking for the tension force in the tie, FTD. And you can put it in one formula, one closed formula, and then FTD is equal to that. The units are kilonewton and millimeter, and NC is a fictitious, not a real compression force, but there's a dimension of a compression force, but it's just to make the formula a little bit more easier to write down. Is equal to this amount. What is now the validity of the model? Well, it has some limitations, and the first limitation, of course, is it should be a D zone. That means that AC must be smaller than Z0. It means that it is a corbel and not a cantilever. And Z0 was equal to this formula here. Then the angle of compression strut, the theta, we know that the Tanger's theta must be between 1 and 2.5. If not, then the dimensions of the corbel are not okay, and the method that we've described here is not right. And the tangents of theta was Z divided by AO plus E. Tie reinforcement. Tie reinforcement is equal to the tension in the tie divided by the yield stress of the steel. We are working in kilonewton and in megapascal. That's why there is a multiplication by 1000, because AS is in millimeters. And FYWD, it's the yield stress of the concrete of the steel, which is the FAK divided by the material coefficient. Horizontal stirrups. Horizontal stirrups we put into the corbel, and the horizontal stirrups is the horizontal force divided by the yield stress. It must always be bigger than the force in the, then the reinforcement in the thigh divided by 4, and the force, the horizontal force, or the force in the horizontal stirrups, I have to say it like that, FWH, it's the force in the horizontal stirrups, is given by this formula. And it must always, this force must be always smaller than FTD, smaller than the tension in the thigh. And it must be positive, of course, because it happens that this gets negative, but then you put the force equal to 0. And horizontal stirrups, you only place it when AC is smaller than HC over 2. In practice, we prefer to put always horizontal stirrups, a certain amount of stirrups. When this condition happens, then you have to put them. Then it's necessary. If this condition is not there, you can put them. And then vertical stirrups, the amount of vertical stirrups is calculated as the force FWV divided by the yield stress. It must be bigger than the total vertical force of half of the total vertical force divided by the yield stress. And the value is given by this formula. Again, it must be smaller than FED and it must be positive. And the vertical strips, you have to apply them when AC is bigger than HC over 2. But AC is always smaller than HC. Then let's see at the construction when AC is smaller than HC over 2. Then you will see that you have horizontal stirrups, and the amount of the stirrups is 1/4 of the main reinforcement. And the main reinforcement is the reinforcement in the thigh on top of it. This is a typical reinforcement for a corbel with AC smaller than 0.5 times HC. When this is not the case, then you need vertical reinforcement, a vertical stirrup reinforcement, and the amount is half of the vertical force. This was a calculation for corbels in ultimate limit state persistent. When we want to do a check in serviceability limit state and we want to limit the maximum crack width, then we can do so in an approximation by using table 7.2n of Eurocode 2 part 1.1, and we will limit the steel stress in the reinforcement according to the diameter we are using and the maximum allowable crack width. For instance, if you only allow a crack width of 0.3 millimeters and you work with a diameter 16, then the maximum stress that you should allow in the steel is 240 megapascal.